Hello everyone, welcome to Chemistry Academy. This is JEE Advanced series where we discuss question to improve your rank in JEE Advanced. Hope this is useful to you. Don't forget to like the video. For more such content, you can download our app. This is episode 25 of JEE Advanced problem series. And this question is based on entropy change and it is given in Irodov. So it's a Irodov problem. In this problem, there is only one part in Irodov and I have added 5 parts more to it, make it more useful for JEE Advance. So I hope that you like this problem. I'm going to share the problem with you. I'm going to read out the problem. You can pause the video and you can try by yourself. So the problem is 1 mole of an ideal gas with the adiabatic constant gamma goes through a polytropic process, as a result of which the absolute temperature of the gas increases tau fold. The polytropic index is equal to X. Find the following if initial temperature of gas is T naught. So the first part is the entropy increment of the gas in this process. And this is the only part which was given in Irodov. Now I have added some more parts to make it more useful to you. The entropy change of surroundings, the entropy change of universe, the internal energy change of system, the enthalpy change of system, the work done during the process. So you can pause now and you can try by yourself. You have to write the answer in the given variables, like in terms of gamma, in terms of tau, in terms of number of moles of the gas, and the temperature T naught, and the polytropic index X. So let us solve this problem one by one. So we are going to solve the first problem, the entropy increment of the gas in this process. Before solving the problem, I will like to discuss about the polytropic process. So what we know about polytropic process, that it is a reversible process followed by an ideal gas whose formula can be written as PV to the power X is constant. Like PV to the power gamma is valid for adiabatic reversible process. It is not valid for irreversible process. Similarly, PV to the power X, where X is polytropic index, is valid for a reversible process followed by an ideal gas. So same way I can write a temperature volume relation, because here they have mentioned about the temperature change. And when we write the formula for entropy change, we can write in terms of temperature change and volume change. So that's why if I write, it is TV to the power X minus 1 is constant, right? So it's very simple here. If you put PV is equal to nRT in place of pressure nRT upon V, and you can take nR on the right hand side. So you can write this as temperature into volume to the power X minus 1 is constant. Now we can write that T2 V2 to the power X minus 1 is equal to T1 V1 to the power X minus 1. From here, if I calculate what is the value of V2 upon V1, so the value of V2 upon V1 is equal to T1 upon T2 to the power 1 upon X minus 1. So what I have done, I have taken this T2 on the right hand side and V1 to the power X minus 1 on the left hand side. So it is V2 upon V1 to the power X minus 1. When I simplify it, it will come T1 upon T2 to the power 1 upon X minus 1. And T2 upon T1, final temperature upon initial temperature, is tau here. So initial temperature upon final temperature is 1 upon tau. So 1 upon tau to the power 1 upon X minus 1. Now already we have derived that if an ideal gas participating in any process, the change in entropy can be written in 3 ways. So I'm writing the first way to calculate entropy change. Entropy change is equal to NCV ln T2 upon T1 plus NR ln V2 upon V1. So now if I put the value of V2 upon V1 in this equation And we know that for an ideal gas, Cp minus Cv is equal to R. So if I divide both sides by Cv, I can write the value of Cv in terms of gamma. So I can write that Cv is equal to R upon gamma minus 1, right? Because if you simplify, left hand side is gamma minus 1. So Cv is equal to R upon gamma minus 1. Now if I put the value of Cv in this equation, then we can write that the entropy change is equal to N into Cv. Cv is equal to R upon gamma minus 1 ln T2 upon T1. So T2 upon T1 is tau plus NR ln V2 upon V1. So when we are writing this ln V2 upon V1, we can put the value of V2 upon V1 is 1 upon tau to the power 1 upon x minus 1. If I simplify this, I can write that this value is equal to nr upon gamma minus 1 ln tau minus nr upon x minus 1 ln tau. So here nr ln tau can be taken common. So we can write that nr ln tau, and this will be 1 upon gamma minus 1 minus 1 upon x minus 1. If I further simplify, I can write that entropy change of the gas means entropy change of the system is equal to nr ln tau. On simplification, I am getting numerator as x minus gamma, 1 will cancel out, upon gamma minus 1 into x minus 1. So this is the entropy change of the system. Now, same way I can calculate that what is the entropy change of the surrounding. Since it is a reversible process, for reversible process, we know that there is no change in entropy of the universe, right? So delta S total is going to be 0. And delta S total is equal to delta S system plus delta S surrounding. Since in case of reversible process, we can always write that there is an equilibrium between system and surrounding. So delta S total is equal to 0. So from there, we can write that entropy change of the surrounding is equal to minus times the entropy change of the system. Already we have calculated the entropy change of the system. So if we put minus sign over here, I can write that this value is equal to minus nr ln tau x minus gamma upon gamma minus 1 and x minus 1, right? So gamma minus 1 multiplied by x. So this is the entropy change of the surrounding. So if I know entropy change of the system, entropy change of the surrounding, right? If we add, we are going to get the value is equal to 0. So this is more easy way to calculate. You can also calculate by another method. You can say that entropy change of the surrounding is equal to Q surrounding upon temperature of the surrounding, and by this method also you can calculate that what is the entropy change. But for that you have to first calculate what is the heat energy exchange by the system, which can be calculated, and heat energy exchange by the system is minus times of heat energy of the surrounding. Nothing is mentioned about the temperature of the surrounding, then you have to assume that the final temperature of the system is equal to temperature of the surrounding, because heat energy is flowing here from the surrounding to the system, which can be possible because temperature is increasing. So heat energy following from the surrounding to the system. So the final temperature of the system is equal to the temperature of the surrounding. That assumption we can take, and we can solve this problem by this method also, but that is a lengthy method. More simple method is this one, right? Because we know that PV to the power X will be valid for reversible process. For reversible process, there is no change in entropy of the universe. So entropy of system is minus times of entropy of the surrounding. Fourth point is the internal energy change of the system. And we know that system is ideal gas, and we have proved that ideal gas participating in any process, the change in internal energy can be written as NCV delta T. So we can put here N is 1 here, and the value of CV we can write as R upon gamma minus 1. Nothing is mentioned about CV. They have given gamma. That's why we are writing in terms of gamma. So R upon gamma minus 1. Delta T means final temperature minus initial temperature. So if initial temperature is T naught, Final temperature is tau times of T naught. So final temperature minus initial temperature, which can be simplified as R tau minus 1 upon gamma minus 1 into T naught. So this is the internal energy change of the system. If we want to calculate what is the enthalpy change of the system, again we can write a direct formula to calculate enthalpy change. Ideal gas participating in any process, enthalpy change can be written as NCP delta T. Now Cp we can use as Cp minus Cv is equal to R. If I divide both sides by Cp, I can write that this value is equal to 1 minus 1 upon gamma. So if I simplify, 1 minus 1 upon gamma is equal to R upon Cp. From there I can write that the value of Cp is equal to gamma upon gamma minus 1 into R. So now I can use in this formula. From here I can write that the enthalpy change is equal to number of moles of the gas given is 1. Cp value is equal to gamma R upon gamma minus 1 into temperature change, that is tau minus 1 T naught. Final temperature minus initial temperature. Final temperature is tau times the initial temperature. So this is enthalpy change. And the sixth part is the work done during the process. So the work done during the process can be calculated by two methods. The first method is very simple, which is based on direct formula. And method one, we can write that work done in polytropic process. Right? I am using the formula to calculate work done in polytropic process. Like it is like adiabatic process, P2V2 minus P1V1 upon x minus 1, where x is the polytropic index. In case of adiabatic, we write that P2V2 minus P1V1 upon gamma minus 1. And by using ideal gas equation, I can also write this as P2V2 is nRT2. So P1V1 is nRT1. So this is nR delta T upon x minus 1. So from here, I can calculate that what is the work done in polytropic process by using the formula directly. So we can write here that work done in polytropic process is equal to, since n is equal to 1, R temperature change can be written as tau minus 1 into T naught upon x minus 1. So this is the work done in polytropic process. This work done can also be calculated by the second method. So in case of method 2, we are using first law of thermodynamics, right? So in case of method 2, we can write that delta U is equal to Q plus W. We have to calculate Q, already calculate work done, right? So for that, we have to calculate Q. In order to calculate Q, we can write that Q is equal to N into Cm into temperature change. So N is 1. So Cm we can write for a polytropic process, Cm is equal to Cv plus R upon 1 minus X. This is the formula for Cm in a polytropic process. Here Cv can be written in terms of gamma. So Cv is equal to R upon gamma minus 1. And this, if I simplify, this can be written as minus R upon X minus 1. So from here we can write that the value of Cm is equal to R, we can take common. So this is coming X minus gamma upon gamma minus 1 into x minus 1. This is the value of Cm. So from there I can write that the value of Q is equal to N is equal to 1. Cm value is equal to R into x minus gamma upon gamma minus 1 into x minus 1. And temperature change can be written as tau minus 1 into T naught. So this is the value of Q. We have already calculated the change in internal energy, that can be written as N into Cv. N is equal to 1. Cv is equal to R upon gamma minus 1 into temperature change, that is tau minus 1 into T naught. So by using first law of thermodynamics, I can write that work done is equal to delta U minus Q. So the value of delta U, here we can put delta U is equal to R upon gamma minus 1 into tau minus 1 T naught, and minus times of Q means we can write here this is r upon gamma minus 1, and this value is equal to x minus gamma upon x minus 1, and this is tau minus 1 into t naught. So now if I simplify from here, I can write that this r upon gamma minus 1, tau minus 1 into t naught I can take common. So this is going to be 1 here, and here we can write x minus gamma upon x minus 1. So now if I simplify this, I'm going to get r tau minus 1 into t naught divided by gamma minus 1. On simplifying this, I'm getting that x will cancel out. So this value is coming gamma minus 1. So gamma minus 1 upon x minus 1. So gamma minus 1 will cancel out. So we are getting the same work done, right, by what we are getting from the first method. This is the same answer what we are getting here, right? So either I am solving by using the first law of thermodynamics, or I am solving by using direct formula of work done. I am getting the same answer. So I'm hoping that this is useful to you. I will request you to please share about our channel in your circle. Thank you very much. Bye bye.